Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 3.3, the inverse of a matrix. In Chapter 3.3, we define the inverse of a square matrix and how to use it to find the unique solution of a given system of equations. We will also see that not all square matrices will have an inverse, in which case we apply methods of Chapter 3.2 to examine solutions of the system. Consider for a moment real numbers. If you were asked the question, 8 times what equals 1, you'd probably say, well, 1/8. 1/8 times 1, 8 times 1/8 is equal to 1. In which case, you'd be telling me the multiplicative inverse. Multiplicative inverse. The multiplicative inverse is a number that you multiply by 8 to get back 1, where 1 is also referred to as the identity. Note that 1 has a very unique property as well, the identity, because we know that 1 times anything is always equal to the anything. It doesn't change anything. So naturally, we want to ask the same thing with matrices. If I were to give you some matrix A and say A times what equals I, where I is the identity matrix, recall the identity matrix would still have the property that I times any matrix is equal to that same matrix. So what matrix would you multiply by A to get I? I'd still want it to be its multiplicative inverse, and we write that as A raised to the -1. Now when I write this, let's make a note, of course, that when we say A to the -1, we mean multiplicative inverse. A to the -1 is not equal to 1 over the matrix A. This arithmetic is not defined with matrices. Let's look at some definitions. If the product of two square n by n matrices, and I'm using this the letters N and N here to say that the matrix must have the same number of rows and the same number of columns. So it's square. If the product of two square n by n matrices is equal to the identity matrix, I, then we say the matrices are inverses of each other. It doesn't matter which one we call the inverse. And they satisfy the property that A times A inverse is equal to I, and A inverse times A is equal to I. So it doesn't matter which order you do the multiplication in here. Another way to say that is with inverses, matrix multiplication is commutative. The order does not matter. In general, matrix multiplication is not commutative. In general, we want to know that some matrix A times some matrix B is not the same as BA. in general. But for inverse matrices, it is. Other terminology that we also use is to say that a matrix A is invertible, or a matrix A is non-singular, or that the determinant of the matrix A is non-zero. Now, we have not covered the determinant yet in our class. It is something you probably saw in a previous college algebra class, but this is something that we'll spend a little bit of time talking about in chapter 3.4. But it felt appropriate to mention it now, as it's a skill that you have probably seen in your past. And lastly, we can say that the rank of A is equal to n, meaning every column is equal to a pivot column. Let's look at an example. Here we're asked to show the following matrices are inverses of each other. And so what we're asked to show is that when you multiply these two matrices together, you will always get back the identity matrix. So let's look at this first one. The matrix 1, 1, 4, 5 times the matrix 5, negative 1, negative 4, 1. We'll do this matrix multiplication. Recall how we do this. Take your first row of A and your first column of B, and that'll give you the product that, or the entry that goes in this first location of our product. So it'll be 1 times 5 is 5, minus 4 is 1. When you want the second entry of your product, so it would be the first row of A times the second column of B. So 1 times negative 1 is negative 1, plus 1 times 1, which would be 0. And I'll let you do the next two multiplications. Okay, I hope you did this. The second column, or the second row of A times the first column of B. This would be 20 minus 20 would be 0. And then our last product would be the second row of A times the second column of B. This would be negative 4 plus 5 gives 1. So notice that we do get back the identity matrix. Check. Okay. Now I'd like you to also check this second product. Check that 5 times, or 5 negative 1, negative 4, 1, so matrix B, times matrix A, verify that this product is equal to I. I'm going to pause the video for just a moment to give you a second to calculate this. I ask you to do the same and then come back and check, make sure we get the same answer. Okay, let's see how you did. I hope you verified that this matrix multiplication also gives you the identity matrix. Check. In which case we can say these are inverse matrices. They are inverses of each other. It does not matter which order you do the matrix multiplication. Let's look at another example. Here we're asked to solve the system of equations using an inverse matrix. To start our process, we will first have to rewrite our system of equations as a matrix equation. So as a matrix equation, let's write the coefficient matrix A first. 1, 1, 4, 5 times a vector of variables. This will equal a vector that's equal to the right-hand side. And written like this, we now have our matrix equation in the form AX equals B. Now, because A inverse exists, we can multiply on the left to obtain, well, let's take our matrix equation AX equals B, and I'm going to multiply on the left by the inverse matrix. And then I'm going to group A inverse and A together. Recognize that A times A inverse, because these are inverse matrices, this has to equal I, the identity matrix. But recall the matrix I has the property that I times anything is equal to the anything, which means this product has to equal just X, which is our solution vector that we're searching to find. So this result tells us to find the solution vector, just multiply B, the right-hand side, by whatever the inverse matrix is. So for our example, we have the solution vector xy is equal to our inverse matrix times 1, 6. And now you're probably thinking, but wait, what is the inverse matrix? And what I'd like you to recall is this matrix 1, 1, 4, 5 looks familiar. And if we actually look back to our previous example, we have shown that the matrix 1, 1, 4, 5 has an inverse, and it's 5, negative 1, negative 4, 1. It's this matrix B. So let's grab that matrix B, which happens to be the inverse of our matrix. So now we're going to multiply by 5, negative 1, negative 4, 1. Now in general, we're going to have to find the inverse matrix on our own, but I constructively ordered these examples to work out nicely for us. Okay, so now let's do our matrix multiplication. So when you multiply your inverse matrix A times 1, 6, notice that the first entry is going to be 5 times 1 is 5. Negative 1 times 6 is negative 6. So it's 5 minus 6 should be negative 1 is our first entry. Similarly, you take your second row of our inverse matrix times the column vector B, be -1 times, -4 times 1 is 4, plus 1 times 6 is 2, or 1 times 6 is 6. This should give us 2. So here we have now our solution is the ordered pair -1, 2. Now, since this is the first example we've done, it might be nice to actually verify this works. So maybe go back to your original system and let's plug in the numbers -1 and 2. Notice that -1 plus 2 does equal 1. And put in -1 for x and 2 for y. So it'd be -4 plus 10, and that does equal 6. And so we can verify that this, yes, is a solution. Okay, in general, there are 3 common methods for finding the inverse matrix. I said common because there are some other methods that you would learn in a strictly linear algebra course. But our focuses will be on solving systems of equations and then relating this to differential equations. So here I'm presenting just these 3 typical methods. So how you find an inverse of a matrix depends on the size of the matrix. Some methods are easier depending for small matrices, and some methods are easier for large matrices. Method 1. If you're given a 2 by 2 matrix, the easiest method for finding the inverse matrix is using this formula. So given some matrix with entries A, B, C, D, then the inverse matrix is 1 divided by the product AD minus BC times a matrix where you swap the main diagonal. So A becomes D, D becomes A. So you swapped these 2 entries. And then you negate the off-diagonal entries. So B and C both become negative. And so this is your shortcut formula for finding the inverse of a matrix. If you're given an n by n matrix, so it must be square, but larger than 2 by 2, we can find the inverse matrix by augmenting the matrix A with the identity matrix I, and then rewriting this new matrix in RREF form. So construct your augmented matrix, write in the matrix in RREF. If the result, and that's where we have to be cautious, is if the result is I times A inverse, meaning this left-hand side now turns into the identity, then the right-hand side will be the inverse matrix. If the left side is not I, then the matrix A does not have an inverse. So they ask us to do this process, and depending on the result, we know if there's an inverse or not. Now, in practice, it's usually easier to first use the determinant to see if A inverse even exists. So recall from our definitions earlier that if your determinant is non-zero, then A inverse exists. So they say, check the determinant. If it's not 0, then use this process to find the inverse matrix. And then our last method that we could use is use the calculator or some other matrix calculator to find the inverse, which is the preferred method of most students. Let's look at an example. let's solve the system of equations here. To start with, you must write it as a matrix equation. So to write this as a matrix equation, I'm looking to write it as AX equals B. So first grab our coefficient matrix. 1, 3, 2, 4 times our vector of variables x, y equals the right-hand side. Now for this matrix A, we want to find the inverse matrix. So for matrix A inverse recall, grab your formula from the previous page. So given some matrix A, the inverse is 1 over AD minus BC times this new matrix. So it's going to be 1 over, now AD is 4, so 1 times 4 minus 2 times 3 times the matrix where you swap the main diagonal entries and negate the off diagonal entries. I think if you simplify this fraction in front, you have 1 times 4 is 4 minus 6 would be negative 1/2. And now if you multiply by a half, I think you get negative 2, 1, positive 1.5, negative 0.5. This is your inverse matrix. So now that we have our inverse matrix, then we know that our solution X must equal the inverse matrix times our right-hand side. It might be a good skill or a good time to practice that this matrix times A really does equal I, but I'm going to leave that for you to verify. So let's grab our inverse. Didn't write this right. That's needed an equal sign here. Oh, that's not -1. That's a +1 there. And this is now negative 0.5. Times 5/8. So now let's do this matrix multiplication. And again, so we'll take this first row of A times B. It might be easier to use a calculator to help you with this. But -2 times 5 is -10. 1.5 times 8 is 12. So -10 plus 12 gives you a first value of 2. And then next calculation, we'll do the second entry which should be the second row of A times 5, 8. So it'll be 1 times 5 is 5, minus 0.5 times 8, which is 4. I think we get 1 as our value. This tells us our solution is the ordered pair 2, 1. Again, maybe it'd be helpful for us to verify that 2, 1 works as we build confidence in our system. So plug in 2 and 1. Notice that you do get back 5. Plug in 2 and 1 for the second equation. Notice you do get 8. And so we can verify that 2, 1 is a solution. Okay, let's try another example. I'd like to give you a moment to work this example on your own. So if you could, please pause the video and look for the inverse matrix. Again, I would encourage you to follow the same write-up as we did in our previous example. So maybe first, write your matrix equation. Show me then how to find A inverse. And I will see you back in just a moment to see how you did. Okay, let's see how you did. So as a matrix equation, I'm hoping you wrote 1, 2, 2, 4 times your vector of variables, x, y, equals 0, 3. So now here you're grabbing your matrix A, 1, 2, 2, 4. So now A inverse would be 1 over. Now, the way I remember this is look at the product. 1 times 4, so the product of the main diagonal, minus the product of the off diagonal, which is 2 times 2, times the matrix, where you swap the entries on the main diagonal, you negate the entries off on the off diagonal. So here you have 1 over. So here you had 1 times 4 is 4, minus 2 times 2 gives 0. And as you know, you can never divide by 0. So this result tells us that the inverse matrix does not exist. We cannot use the inverse matrix for this problem. Now, it doesn't mean that the problem is not solvable, though. What it means is that I cannot solve it using the inverse matrix. So when the inverse matrix method fails us, we will now resort to the Gauss-Jordan elimination method. So now we're resorting to the methods that we learned in chapter 3.2. So recall, for the Gauss-Jordan elimination method, we will write our augmented matrix AB. One, two, 2, 4. And I like separating my right-hand side with a straight line just to identify that the left side is the coefficient matrix, the right side is my solution vector. And remember, with the Gauss-Jordan elimination method, we seek to have a pivot in this first position and then use that pivot to make what's below this turn into 0 using our elementary row operations. So here I'll say, what if we did -2 times row 1 plus row 2? And we would have, when doing this, the first row would not change. And then -2 times 1 is 2, added to 2 is 0. -2 times 2 added to 4 is 0. -2 times 0 added to 3 is 3. And our matrix is now in reduced row echelon form. But what I think we should identify that's really important is we have this bottom row with 3 at the end. Recall what this is interpreted to mean is 0x plus 0y equals 3. Of course, this doesn't make any sense, and so we need to interpret this to mean that there are no solutions to this system of equations. However, if just let's hypothetically say if this 3 were 0, then we would have infinite solutions to this system of equations, and we would still be solving it using this method that we're illustrating now. Okay, let's try another example. Let's solve the system of equations given. In this example, let's practice the augmented matrix method. Meaning, let's augment our coefficient matrix A with the identity matrix. So our coefficient matrix A would be 1, 1, 1, 2, 2, 0, 3, 4, -1, augmented with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And now we'll transform this augmented matrix into RREF. Now I do not want to do this by hand, so I'm going to grab my calculator to help me with this. And let's first enter in our augmented matrix. So recall the matrix key is located underneath the x to the -1 button here. In mine, it's in blue, so I have to hit second x to the -1 to get to my matrix menu. We're going to edit a matrix. It doesn't matter which one we edit. I'm going to edit matrix A. And let's first enter in our the size of the matrix is we have a 3 by 6, 3 rows, 6 columns. And let's enter in the values of the matrix. I'm going to go in rows. And after you enter in your matrix, take a moment and look through the entries just to make sure you didn't make any errors. It'd be terrible to continue on with an error in how you entered your matrix. I'm going to look at mine by going down the columns. 1, 2, 3. And I'm comparing it to my augmented matrix over here. Then there's 1, 2, 4, 1, 0, negative 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so I've entered my augmented matrix. I'm now going to go back to my home screen by hitting second quit. And now I want to do some matrix math. So go back into your matrix menu by hitting second matrix. Choose our math option. And remember, RREF is at the bottom of this list. You can arrow down or you can arrow up to get to the bottom quickly. So choose option B, RREF. Tell it that we're working on the matrix A. So let's enter in second matrix and choose option A. Put a parenthesis. When we ask for the reduced row echelon form of the matrix A, we get this matrix. Let's go ahead and write that matrix down. So you get 1, 0, 0. Put my calculator back on so I can verify I entered this, wrote this down correctly. Looks like I got it right. So now what we'd like to identify is that because the left-hand side is I, that tells us this right-hand side is the inverse matrix. So now let's use this inverse matrix to find the solutions to our original system of equations. So let's start by writing first our matrix equation. So here our matrix equation is going to look like 1, 1, 1, 2, 2, 0, 3, 4, negative 1 times our vector of variables, x, y, z, and this has to equal our right-hand side, 1, 6, 13. Now that we have our equation written as a matrix equation, AX equals B, we're going to use the fact that we know that our solution vector X has to be found by looking at A inverse B. So now here X, Y, Z are vector of variables. Let's grab our inverse matrix. Negative 1, 2.5, negative 1, 1, negative 2, 1, 1, negative 0.5, 0. And we'll multiply this times our column vector B. To find our solution. Now I know we can multiply this by hand. I'm going to grab my calculator to help me with this so I don't make any simple multiplication errors. But we should be going this first row of A inverse times B. So I think this is going to be -1 times 1 plus, let me grab my calculator. I'll do it with you right here. -1 times 1 plus 2.5 times 6 minus 1 times 13. And you should get back 1. Let me turn my calculator back on. For the second entry, it would be 1 times 1 minus 2 times 6 plus 1 times 13. So here I'm looking at the second row of A times our column vector. And I believe we should get 2. Okay, we have one more to do. We'll do the third row of our matrix A inverse. So now 1 times 1 minus 0.5 times 6 plus 0 times 13. Not sure why I'm writing that 0 in there. I already knew it was 0. And this should come back with a -2. This tells us our one unique solution that we have for our system of equations is the ordered triple 1, 2, -2. And again, as we're building confidence with our method, it might be nice to go back to original system of equations and try plugging in 1, 2, -2 and verify this really does equal 1. Plug in 1 and 2 into your second equation. Verify that really does equal 6. 1, 2, -2. And verify that really does equal 13. So that we can be confident that our ordered triple 1, 2, -2 really is a solution to our system of equations. Okay, let's do one more example. Let's solve another system of equations. And in this example, it's very similar to the last one, but I'm not going to use the augmented matrix. I am strictly going to use my TI calculator. To find the inverse matrix. However, you can use any matrix calculator to do this. But it's just a different technique that I want to show you. Let's first start by writing our matrix equation. Our matrix equation 1, 1, 1, 2, -3, -1, -1, 2, 2, times our vector of variables. And this will have to equal our right-hand side. So now our system is in the form AX equals B. Now our calculator is pretty great with finding the inverse matrix. And so I can actually do it with just a couple of button pressing. So let's grab our TI calculator. And again, let's enter in our inverse matrix. So to enter in your inverse matrix, remember it's under the x to the negative 1 key. So second A inverse, or x to the negative 1. And again, let's manipulate matrix A just because it's here. Oh, I didn't edit it. Let me start over. So second matrix key, arrow over to edit. And currently it's a 3 by 6, so let's change it to be a 3 by 3 matrix. And take a moment to make sure you entered the correct 3 by 3 matrix in. I'm going to verify I did it by reading down my columns. So 1, 2, negative 1, 1, negative 3, 2, 1, negative 1, 2. And now I'm going to go back to my home screen. And there's two ways you can find the inverse matrix with your calculator. First, grab your matrix. So second matrix and choose matrix A. And then calculate or put in the x to the negative 1 button here. Now I know we said this does not interpret meaning a fraction. It does mean inverse with matrices. So this is asking me for the inverse matrix. And it gives me back all these decimals that I'd rather not work with. So to turn these into fractions, I'm going to hit the math key and choose to rewrite my answer as fractions, which is option 1. And this gives us our inverse matrix. So maybe go ahead and jot this matrix down. Let me bring back my calculator so we can verify we did this correctly. I'm going to read down my columns: 2/3, 1/2, negative 1/6, 0, negative 1/2, positive 1/2, negative 1/3, negative 1/2, 5/6. Okay, we got it right. Okay. So now this is our inverse matrix. So now let's use it to find our solution. So now remember, our solution is going to have to be x equals A inverse B. So if I write that over here, then our vector x, y, z, our vector of variables, times our right-hand vector b, this should be our solution. Now I'm going to try and be a little bit fancy with my calculator. So I know I can do this matrix multiplication by hand like we did in our last example, But our calculator has already stored this inverse matrix as one of its answers. And so what I'm going to do is I'm going to hit the stow button and ask it to stow this as matrix C, maybe. So hit now the second math key, and, oh, not second math, I meant second matrix, and have it stow it in matrix C's spot. Currently matrix C is a 2x3, but this will overwrite that matrix that's written with the one that we just calculated. So now the great thing is, next time you come back and you grab matrix C, matrix C is our inverse matrix that we found. So what I want to now do is let our calculator have this as our matrix C that we entered. We still need to have this matrix B entered in here. So let's go enter this one in matrix B in our calculator, and then we'll have the calculator do the matrix multiplication. So let's go back into second matrix. Let's go edit matrix B. It's a 3x1, which I'm okay with. And let's enter in the values 3, -8, and 3. We'll go back to our home screen, and we're going to grab matrix C, which is currently our inverse, and multiply this by matrix B. So second matrix, pick option B, which is number 2. And now it's going to compute this matrix multiplication for us. And it gives us back the solution. Oh, I didn't want that in red. That doesn't look right. It gives us back, what was that solution? I covered it up. 1, 4, -2. So our solution is the ordered triple 1, 4, -2. Okay, I've shown you several methods now for calculating the inverse matrix and how to use it for solving a system of equations. I'm going to end this video here now. I hope this is helpful, but I'll see you next time.